Welcome, everyone. In this lesson, we're going to start looking at the directional derivative. And we'll probably get to the gradient vector part in class. So first, let's start with the definition of our directional derivative. And we're actually going to kind of approach this using what we've seen before so far. And that is our partial derivatives. So let's suppose that we have a function z equal to f of xy. And we've seen the partial derivative of our function with respect to x, and we've seen how to calculate our partial derivative of our function with respect to y. And it turns out that really what we're doing for both of these partial derivatives is kind of like our limit definition of derivative here. So in the first case, what we're doing with these derivatives is we're really looking at how our function z changes. So we're looking at the rate of change of our function z. And when we talk about the x partial derivative, what we're really doing is we're looking in the x direction. So we're looking at the rate of change of our function as we kind of take a small step in the x direction. And then our y partial derivative is, well, we're looking at the change in our function as we take a small step in the y direction. So to kind of picture what's going on, let's kind of imagine our xy plane. And let's pick a kind of an arbitrary point somewhere on the plane here. So let's call it, let's call this point x0, y0, just some arbitrary point. And at that specific point, we kind of have two directions that are kind of inherited from the grid system. We have our x direction, and we have the y direction. So we have the unit vector in each of those directions. So for our y direction vector, that would be 0, 1. And for our x direction vector, that would be 1, 0. So we have the two unit vectors in either the x direction or the y direction. And essentially what we're doing with these kind of limits here is, like we said, we're looking at what happens when we take a small step. So let's just kind of consider the x case. So we're going to take a small step in the x direction. And what happens is we go from the function value f of x0, y0. So we're kind of looking at the function at that specific point, and then we're going to see what happens to our function as we take a small step in the x direction. So we're going to go in this direction. And what happens is we go from this function value to So we're taking a small step in the x direction, so we're adding a copy of h on. And then our y is going to stay constant. So if we look at this, I've kind of just rewritten these two values here. So we have our kind of our starting function value before we take the small step, and then we have our kind of our ending function value after we take that small step. And I've added a little bit extra in here. So we're taking a small step h, and the constant here is 1 because we're taking a small step in the x direction, and over here in the y direction, we're kind of staying constant there, so I have a 0. And so you can kind of see that we have the x coordinate of 1 for our unit vector is the constant here that I'm multiplying by our small step size. And then the 0 is the 0 that shows up there. And so what we're doing is we're kind of looking at the change in our function as we take a small step in the x direction, and that vector that gives us the direction is actually kind of showing up in this limit calculation. Even though it didn't really look like it at first, that vector is really showing up here. And this is going to lead us to our definition. So let's take a look at our directional derivative. And the setup for this is we're looking at the change in our function if we kind of go in an arbitrary direction. So we have some options here if we're standing at a point P on our graph. So let's see here. Here's our point P. So imagine we're on our surface, we're standing at that point. Well, what we've seen so far is that we can see what happens to the height of my function as I take a step in the x direction. I could look at what happens in the y direction, but now we're going to look at what happens if we take an arbitrary direction. So maybe something kind of in the middle there. And what we're going to see is that we can kind of think of this as measuring the rate of change in an arbitrary direction. So imagine kind of standing at this point P. We have our x direction, which is given by the vector we have our x direction, which is given by the vector 1, 0, if we're at that point P. We have our y direction, which is given by the vector 0, 1. And now we're going to look at an arbitrary direction. And this is going to be, well, we're going to leave it AB. And so what's going on is when we look at when we look at this derivative that we're going to see in this arbitrary direction, essentially we're going to look at the plane we're going to look at the intersection of our surface with the plane that runs kind of through that direction vector and also contains the unit vector in the z direction. So we're going to have this curve that kind of intersects our surface and so we have this curve that sits on our surface that kind of is in this direction, and we're looking at essentially the derivative, the slope of that curve at our point. And we've done this for the curve in the x direction, and we've done this for the curve in the y direction, and now we're going to see what happens if we look at the slope of the curve in an arbitrary direction. And this is our directional derivative. So let's look at the definition here. So first of all, the notation here is we're going to have a unit vector, which we'll call u for unit vector, and it'll have components a and b. And we're looking at a specific point, so x0, y0 here. And so we call the directional derivative of our function f in this direction given by vector u. And we're evaluating at this specific point x0, y0. And this is the kind of the similar setup here for our limit, where we looked at the x partial and the y partial. But now we're letting kind of x vary by a little bit, and we're letting y vary by a little bit. And we can kind of see, if we think about our, again, let's kind of, let's draw our xy plane again. And again, kind of let's center this at our specific point, x0, y0. So we could look at the unit vector in the y direction, which we've seen as just vector j. We could look at the unit vector in the x direction, which we've seen as vector I. And it's 1, 0. But now there's kind of a whole unit circle of vectors that we could look at that completely circle around our specific point. So we have kind of a whole unit circle of possible directions to go in. And so, you know, as this little example, maybe this was the direction we were kind of setting up for our directional derivative here, and this would have components a and b. Now, one other thing, when we specify a direction, we can specify the unit vector as just the vector, or sometimes we might specify the angle. So the angle is theta, and it's the angle between our direction vector and kind of where the x-axis is, or where the x-axis would be. And so this definition, this limit here, this is, if we're going in the I direction, then this just becomes our x partial derivative. And if our direction is in the kind of the y direction, then this just becomes the y partial derivative. So just a quick note here. We've kind of seen this two special cases. So if our unit vector is I, vector I, then this directional derivative is actually just the x partial derivative. And if the unit vector is vector j, well then this directional derivative would be the y partial derivative. So we've kind of seen two special cases of our directional derivative. So let's try an example. And we're going to see how to actually calculate our directional derivative so that we don't have to always go back to this limit definition. And it turns out that not only are these two partial derivatives, f partial x and f partial y, kind of special cases, but they kind of give us a way to help calculate the direction derivative for any direction vector. And so we have this result here that says if our function is differentiable in terms of x and y, then the function has a directional derivative in the direction of any unit vector. So kind of 360-degree option there. We have the directional derivative in any possible direction we want. And the way we can calculate it, so the directional derivative in the direction of vector u, is our x partial derivative times the x component of our unit vector, plus the y partial derivative times the y component of our unit vector. And we're going to actually come back and prove this in a second, but let's actually try a calculation using this result first. So let's find the directional derivative of our function f of xy, where the function here is x cubed minus 3xy plus 4y squared. So that's our function. And we're going to look in the direction of vector u, where u is the unit vector where we specify the angle here. So theta equal to pi over 6. And so this is a fairly common way to specify a unit vector. So it's going to help us to remember how do we find the unit vector if we're given an angle. And so we kind of use our standard polar coordinates set up here. So kind of parameterizing the unit circle, the x component is cosine of theta, and the y component is sine of theta. So we've seen that before with polar coordinates. And this cosine theta, sine theta, this always gives us a unit vector. And so we can find the unit vector in this case since we know the angle. So for us, let's actually work that out. So our directional vector, u, is going to be cosine of pi over, make that look a little better, cosine of pi over 6 and sine of pi over 6. So we're just plugging our angle in. And cosine of pi over 6, sine of pi over 6, these actually have nice values. So cosine of pi over 6 is square root 3 over 2, and sine of pi over 6 is 1/2. So this is going to be kind of the a part of our unit vector, and then we have the b part of our unit vector here. All right, so let's kind of try out. Let's calculate our our directional derivative, and we'll keep that result in mind. So first, let's just write out the formula. So for a directional derivative of a function, we take the x partial derivative of our function, and then we multiply it by the a component of our unit vector. And then we take the y partial derivative of our function and multiply it by the second component of our unit vector. So if we actually calculate the partial derivatives, let's look at the partial derivative for x. Let's calculate that. So for the first term here, that would be a 3x squared. Then we get to the second term, and the derivative of the x there is 1, so we're going to have our minus 3y left. And then for the last term, plus 4y squared, there's no x, so that just would differentiate to 0 when we're doing our x derivative. And then while we're at it, let's fill in the a value. So the a value is this square root 3 over 2. So we fill that in. And then we play the same game for our y partial derivative. So let's go through, do that. And it doesn't hurt, pause the video for a second, try to get it yourself. But when we do our y partial, first term, there's no y. So that's just going to differentiate to 0. Then in the second term, differentiate the y, we get 1, but we're still going to have that minus 3x. So let's write that down. And then for our last term, just differentiate like usual, we get plus 8y. And then if we throw in our b value, we see that the b value there was 1/2. So the y component of our directional vector. And that's it. So that's our directional derivative. And so now this is a function that we could, and there's maybe a little simplifying we could do. So, you want to try to look for terms that maybe you could combine. Really the only thing, we're not going to, if we multiplied all this out, same thing over here, multiplied all this out, we're not going to be able to combine the 3x squared or the negative 3x because it's different powers of x. We would technically be able to do a little simplifying with these y terms though. But we're just going to leave it like this. Now this is just a kind of a regular scalar valued function. So when we plug an x and y value into this, we should get a number out. So let's see what happens if we evaluate this directional derivative when at the specific point x equal to 1 and y equal to 2. So we're going to calculate this directional derivative evaluated at the point 1, 2. So we're going to use this formula we just figured out, and wherever I see an x, I'm going to plug in 1. And wherever I see a y, I'm going to plug in 2. So when we do this, get 3 times 1 squared minus 3 times 2 times our square root 3 over 2. And then let's do the minus 3 times x, so minus 3 times 1, plus 8 times 2, and then our times 1/2. So again, we're just plugging in here. Wherever I see an x, I plugged in 1, and then wherever I saw y, I plugged in 2. And if we do the calculation, I think we're going to end up with, let's see, we're going to end up with negative 3 times square root 3 over 2. Yep. And then plus, and then this is going to be 13, so 13 over 2. And if we wanted to, we could get a common denominator and add these together, but perfectly fine. So we get a number for our directional derivative once we evaluate. All right, so this is telling us how much the height of our function is changing as we take a small step in this direction. All right, so let's back up and let's see just kind of maybe a quick proof of this formula. So how does this work? So we're going to define a function in terms of vector 8, or in terms of that number h, that variable h. And our function here is going to be the function value, where the function f in this case, where we're looking at that specific point x0, y0, and we're taking a small step in both the x and y directions. So this function right here is the same, if we go back up, is this part right here of our definition. So that's all we're doing, is we're saying this part is kind of a special function in terms of h. And turns out that g, this function g, which has h as its variable, is a real valued function. So it's a one variable function. So Calc 1 derivative applies. So we can calculate the derivative of this directly at h equals 0 by doing our limit definition. As h goes to 0, g of h minus g of 0 all over h. And if we kind of fill in the value of g of h here, we're going to end up with the limit h going to 0, f of x0 plus ha, y0 plus hb, and that's precisely what g of h is. So that's this part. And then g of 0, if we plug 0 in for h, this part's going to be gone and that part's going to be gone. So it's just going to be our original function evaluated at x0, y0. And then this is all over h. And this is precisely the directional derivative of our function evaluated at x0, y0. A little tight on space there. All right, so we have, so far, we're looking at this side of the equation of the formula. All right, so where does the action happen here? So far, we're not done yet. We have this function g of h, and we're saying that if we do our Calc 1 derivative, we can think of g prime of 0 as being this directional derivative. Well, it turns out that we can also view g as a composition of functions. So it's a composite function. So essentially, g of h is equal to f of xy, where x is an inner function, and it's x0 plus ha, and y is also an inner function, and it's y0 plus hb. So when we have a composite function, we have an outer function f, and we have two inner functions here. Chain rule is going to apply. So our chain rule applies here. So when we calculate the derivative, say the derivative at any h value, well, if we apply our chain rule, it's going to be the partial derivative of f with respect to x times the partial derivative of x with respect to h plus the partial derivative of f with respect to y times the partial derivative of y with respect to h. And so this is just the chain rule we looked at for the case 1 chain rule that we looked at last time. And if we calculate the partial derivative of x with respect to h, the x0 is just a constant. Derivative of h is 1, so we're just going to have the a left over. So if we fill this in, we're going to have our x partial derivative times a, and then we have our y partial derivative. And if we look at the partial derivative of y with respect to h, again, y0 is a constant because it's just a specific point. Derivative of h is 1, and then we still have the b there. So this is times b. And so what we've shown is that when we look at specifically g prime of 0 here, we have f partial x evaluated at our specific point times a plus f partial y evaluated at our specific point times b. And so what we've just shown is that if we view this kind of special function here, or special kind of view of this function as a real valued function, we can calculate the derivative just like we would have in Calc 1, and we get this formula which tells us g prime of 0 can be viewed as the directional derivative. But if we view g as a composition of functions and use chain rule, then we get this alternative formula here. And it turns out g prime of 0 is equal to both of these values. So they're equal to each other. So kind of an interesting proof there, because we get to use our chain rule, and we get to use the always popular there limit definition of derivative. All right, so we're going to stop there, and we're going to see next time, well, we'll do a few more examples, but next time in class, we're going to get to this gradient vector, and we'll talk more about that. So we'll see you then. Bye-bye.